today I want to talk about some work most that is joined with Alex Kumjian, Jean Renaud, Aidan Sims, and Dana Williams. And this is a construction that we realized showed up in at least a couple of our papers. And I wanted just to highlight in case some other people might find it useful in their constructions. And I want to emphasize this is probably not the most technical part of our proofs or our theorems, but it's just that we realized for at least one project later on that some of our constructions, they all fell into this so-called push-up construction. So I'm going to start with the definitions of groupoid extension and define what the push-out is, and then the goal is to provide the free application of these constructions. Once again, the theorems that I'm going to cite, most of them, at least the most important ones, will be really without the proof, because this construction, as I mentioned, it just plays a small part, but it doesn't really necessarily help with the proofs themselves. So the setup that will be, so we'll have, I hope there have been quite a few talks on groupoids, so I hope most of you are familiar with this notion. So I'm just going to assume, so in our work, we assume locally compact Hausdorff groupoids. For the definition of the push-out, we don't need a Haar measure. Once we start discussing about applications to sister algebras, then we are going to add the condition of a Haar system. But for now, just a topological, and we locally compact abelian group bundle. So with script letter A, we call such a group bundle a G bundle for the groupoid if the groupoid G acts on the left of the group bundle by automorphism. Okay, so once we have, now we talk about an extension, and this definition generalizes previous definitions due to Kumjian, Tu, and probably others. So we have a groupoid G, a locally compact abelian group bundle A, and an extension of A by G is basically another groupoid sigma. And we have this diagram, or we have an inclusion and a projection map, and the unit space is preserved. And we assume that P is a continuous and open map. I is a homeomorphism to its range. And if the action of G on A basically is given by the conjugation, we call the extension to be compatible. And this will be the main object, the type of object that we'll study. So let me provide, there are no questions, two examples. One, just probably the easiest one that can be the semi-direct product. So if we have, you just take elements, the fiber product of A and G, fibered by P and R, and with the natural operation, so you want the source of gamma 1 to equal the range of gamma 2, and which means you can act gamma 1 on A2. So, since we assume, I want to say that, since A is abelian, consists of abelian groups, we are going to write the notation abelian groups as addition. So that's why we have that plus and minus here. So this is the natural operations for the semi-direct product. And the second important example is when we have a two cocycle, and in this case we assume that the group bundle is the trivial group bundle A class G0, where A is just an abelian locally compact group. And we have normalized two cocycle from the groupoid into A. Then such a two cocycle defines a natural extension that we call it sigma phi, The notation will be important in a few slides. And basically, once again, we look at the product A cross G and the natural operation. So we add on the fibers and we twist by the cocycle when we add, and also we twist by the cocycle when we take the inverse. Okay, so next is the definition of the properly isomorphism, because when this is the natural set to compared to extensions. So we have two extensions, sigma 1 and sigma 2 of A of the same group bundle by the same groupoid G are called properly isomorphism if we can find a groupoid isomorphism from sigma 1 into sigma 2 such that this diagram commutes. Again, don't forget that all of this has to be unispace preserving. So the unispace of A, sigma, and G1, sigma 2, and G are all the same. Okay? And now the collection of proper isomorphism classes, we call it TG of A, and will denote the equivalence class, the proper equivalence class of an extension by right brackets of sigma. So now the theorem that in our work we generalized Alex work when he worked in the et al. Case, and namely that if we have now, so we have two locally compact abelian groups A and B, and we have a continuous G equivariant map from A to B, and now if we start with sigma as an extension of A by G, the idea is we can push it basically in a unique way to extension by B. Okay, so there is an extension F star sigma and natural groupoid homomorphism that makes this diagram commute, and this are uniquely determined up to proper isomorphism. And this is basically the what we call the push-out construction. You have one extension by a locally compact abelian group bundle, and you can push it to push out to an extension over a different locally compact abelian group bundle. So one quick application of this. Before that, we actually provide, following Alex proof from 88, concrete description of the groupoid, and namely one will just start with the fiber groupoid, so the second group bundle, the groupoid G and fiber by sigma, and you realize that inside D lives a natural normal subgroupoid, namely the image of A under this map, whatever. So you can embed naturally A into D, and that turns out to be a normal subgroupoid of D, and the push out is just the quotient of D by this image. So again, the point is that there is a fairly concrete description of the groupoid. So the quick application, just to show it makes proving, so it's well known. Other people have proved it before in various cases, but that the collection of equivalence classes of extension is a group, and the push-out construction gives, in my opinion, probably the easiest way to define group operation in this collection. So namely, basically, if you want to define the addition of two groups, you just define this map from the bundle A cross A into A, and then define the sum of sigma plus sigma prime to be the push out under this map of this fibered groupoid. There is, similarly a clear way how to define the inverse using the push-out construction, and using it, then it follows that indeed TG of A is an abelian group and the neutral element is the class of the semi-direct product. And as I said, the inverse, while I didn't really define it, it's just a push out by taking the map from A to A goes to A inverse. Okay, so that provides a relatively in my opinion, easy to see proof of this fact. Now, the main application that I want to talk, actually, now we come back to sister algebras, are basically that when we have such an extension, there is a natural T-groupoid associated, and will basically provide the isomorphism of the original sister algebra of sigma and reduced sister algebra of this T-groupoid. Okay, so let me go, describe the steps needed to define. So we start once again, we have A sigma G, we have an extension, and basically at this point we're going to require a Haar system. So A has a Haar system, sigma has a Haar system, and then there is a natural way to define a Haar system on G. And we want A now to be wide. I mean, that was the condition from the beginning. Wide just means the unit space of A is the same as all the other. But now, since A is abelian, the sister algebra is abelian, so if you look at the dual, we can view it as an abelian group bundle over G0. Okay, so we can, since it has a Haar system, we can actually view it as a G bundle. So we can take the fiber A hat star A, and this will also be a G bundle. So we started with this extension, the extension of A by G sigma, such an extension. And naturally, if A is abelian and has a Haar system, we can get this bundle. And moreover, there is a natural action of sigma. So sigma acts on A hat, and this action descends to an action of G on A hat in a natural way, and therefore we can form the action groupoids A cross G and A cross sigma, and we get naturally a new extension now over of this G bundle by this groupoid. Okay, so again, from A sigma G, we naturally get this new extension, this new extension A cross sigma. But now, since again we have commutativity here, there is a natural map. So let me again write what the last relation from the previous slide. So we have an extension. Sigma A G, and now there is a map F, a natural map from A cross hat into A hat times T, given by the natural formula, and therefore one can easily check this is equivariant and continuous. So we must have a push out groupoid over of this new group bundle. Okay, so we have, and we are call it sigma hat, this push out extension by this map F. And in particular, one will realize that this is a T-groupoid, also called a twist, is defined by Alex. And based on our proof, our construction, it's easy to actually describe sigma basically triplets exist sigma, where if you recall, we had to mod out by a normal subgroup, and modding out here just means, you know, you take the action of A from sigma onto Z like this, and the maps, just for emphasis, the maps that makes this indeed an extension are once again natural. Everything is natural, but again, sigma dot is just P of sigma from the original sequence, from the original extension. Once again, everything is follows naturally, and as I said, one of the main results in a recent paper that we submitted for publication is far-reaching, I think, generalization of a result due to Muley, Renault, and William from their CCR free paper from '96, and namely, so if we have if sigma is a second countable locally compact groupoid Haar system, so again we still the same setup A sigma G. So A is abelian and has a Haar system. Sigma has a Haar system. Then the Caesar algebra sigma of the full Caesar algebra is isomorphic to the restricted Caesar algebra of the twist, and so this result was proved in '96, as I said, under the restricted assumption that A was the isotropic group bundle, that G was the principal, and C star of sigma was CCR. So the continuous trace Caesar algebra paper, sorry, three. And in addition, we managed to prove that the isomorphism that we define also descends to an isomorphism of the reduced C-star algebras at the reduced level as well. Okay. All right, so next I apply this construction to the two cocycle that I mentioned before. Recall that if you have a two cocycle, there was a extension that I call a sigma phi, a natural extension. And the first observation that is helpful is that if you have a group homomorphism and you do the push out of sigma phi under F, that you get a natural two cocycle, and the push out is properly isomorphic to the extension of this new two cocycle, the B-value two cocycle. And moreover, once again, we can provide an explicit characterization, description of the T groupoid, and the T groupoid of two cocycle turns out it's also defined by a two cocycle, and the two cocycle has a explicit formula. So again, if there are, it's too long, but you see the original cocycle, and it's just taking the more or less Gelfand transform there. So there is a natural construction. So the last couple minute or so, let me just get to the work that we've done. Again, we realized after, so this is based on a paper that already appeared in JOT. So for a concrete example, if we take a second countable locally compact Hausdorff space, and G now is a group, but you see it's a script Roman G, and we start with a Czech cocycle, to normalize two Czech cocycle for some finite cover. Then one will get a natural groupoid, sometimes called a blow-up groupoid, where you look at triplets IXJ, such that exits nu I intersect UJ with very natural groupoid operations. And the Czech two cocycle defines naturally groupoid two cocycle. Okay, so we can look at the extension of phi C, and basically we just write sigma C instead of sigma phi C. But as I said before, this is the push out will be a groupoid, also an extension given by a two cocycle, and the two cocycle is given once again explicitly in terms of the Czech cocycle. And what we proved was a generalization of the Rayburn-Taylor, so the Rayburn-Taylor construction of continuous trace-star algebra. They basically work with the case where G was the torus T. We extended their construction to arbitrary abelian groups G, and basically what we prove that C-star algebra of the twist sigma C has continuous trace. We identified the spectrum, and this map, this two cocycle, basically the class of this two cocycle provides the Dix-Mie Duadie class of the C-star algebra of sigma C. So once again, all the proofs of the Pushout construction is just the getting the description of the theorem, proving though that, as I said, requires different, of course, tools. But I'll stop there since I think I'm already out of time. These are just some references that I mentioned in my papers.